Hello and welcome to Nighttime Science. Tonight we are leaving the familiar world behind once again, not by sinking beneath the oceans but by drifting upward, away from the ground, away from the cities and away from the comforting glow of the sun. We are going to travel into the quiet dark above the atmosphere, into a realm where stars and nebulae glow with a soft and ancient light. There is nothing you need to do right now except to rest and listen. Find a comfortable position. Let your breathing become slow and gentle and allow the weight of the day to settle down and away from you. As you listen, you can simply let the words wash over you like a slow and predictable tide, steady and unhurried. As this journey begins, imagine yourself lying back beneath a clear night sky. At first, you might see only a few bright stars, the most obvious points of light that your eyes pick out automatically. But as your gaze softens and your attention becomes calm and quiet, more stars start to appear. Tiny points of light reveal themselves one by one as if the sky is slowly exhaling and showing you more of what has always been there. Each star is small to your eyes, just a pinprick on a dark canvas, yet each one is enormous in reality, a distant sphere of hot, glowing gas held together by gravity and powered by nuclear fusion at its core. Many of them are so far away that their light has been traveling toward you for decades, centuries, or even thousands of years. The gentle shimmer you see is an echo from deep time. As your awareness settles, imagine that the darkness between the stars is not truly empty. Within that darkness, spread over unimaginable distances, there are immense clouds of gas and dust known as nebulae. To the unaided eye, they are usually invisible, too faint and diffuse to stand out. But they are there, suspended in the great quiet between stars. Some of these clouds cradle the earliest stages of star birth. Others are the delicate remains of stars that have ended their lives and returned their material to space. Let your mind drift from the crisp, sharp points of starlight to these softer, hidden shapes. Imagine a region of space where the darkness seems to lighten into a faint, glowing mist. This is a nebula, a place where hydrogen gas, helium, and traces of heavier elements gather together. In some nebulae, energetic young stars bathe the gas with intense ultraviolet light, causing it to glow in gentle shades of red and pink. In others, the gas does not shine by itself, but quietly reflects the light of nearby stars, taking on a cooler bluish tone. As you breathe slowly in and out, picture yourself floating weightlessly at the edge of one of these clouds. There is no wind, no sound, and no sensation of up or down. The nearest star might be many trillions of kilometers away, and yet its light still arrives, softened by distance. Ahead of you, vast curtains of gas drift like slow, luminous fog, sculpted over millions of years by gravity, radiation, and the gentle push of stellar winds. Far away, a young star is forming in the depths of the cloud. You cannot see it directly because it is wrapped in layers of dust and gas, but you can imagine its presence. Deep within a colder, denser knot of material, gravity is pulling atoms inward, causing the center to grow hotter and denser over long stretches of time. One day, when conditions in the core become extreme enough, nuclear fusion will begin, and that hidden object will shine as a new star. For now, it is still in its quiet, embryonic phase, a protostar slowly gathering mass. Around that forming star, there may be a flattened disk of gas and dust, gently circling like a slow, pale ring. Within that disk, particles drift, collide, and gradually stick together. Over millions of years, some of those clumps will grow into planets, moons, and smaller bodies. The process is unhurried. Every step in the birth of a star and its surrounding system unfolds on timescales that are measured not in minutes or hours, but in millions of years. In this way, the cosmos moves at a pace far beyond any human schedule. As you listen, you might notice how calm these processes feel when imagined in your mind. Stars are born, live, and eventually die, but they do so on a scale so vast that even dramatic events become gentle when viewed from a distance. A star that will one day swell into a red giant is right now in a long and stable phase of its life, quietly fusing hydrogen into helium in its core, maintaining a delicate balance between the inward pull of gravity and the outward pressure of its hot interior. Our own sun is one such star, an ordinary middle-aged star in a long, steady phase of its existence. It has been shining for billions of years already and has billions more to go in this main stage of its life. Night after night, without any effort on our part, its light reflects off the moon, scatters in the atmosphere at dawn and dusk, and supports the conditions that make life on Earth possible. To the universe, the sun is just one star among many, but to us it is the quiet, reliable source of warmth and light that defines our days. Far beyond the sun, however, there are stars that differ in size, color, and temperature. Some are cooler and dimmer, glowing with a deep red hue. Others are much hotter and brighter, shining white or blue. The color of a star tells us something about its surface temperature. Red stars are cooler than the sun, while blue stars are hotter. Yet regardless of their temperature, each star is a sphere of gas bound by its own gravity, a place where matter is compressed and heated until fusion reactions take place in a continuous, steady way. These different types of stars live different kinds of lives. Smaller, cooler stars burn their fuel slowly and can shine for tens or even hundreds of billions of years. Larger, more massive stars live fast and bright lives, using up their fuel quickly and ending in powerful, energetic events. But even those endings, supernova explosions that briefly outshine entire galaxies, are part of a long and gentle cycle. Once the bright flash is over, the expanding material drifts outward, spreading into space and forming delicate clouds that will, over time, merge back into the interstellar medium. Those expanding clouds are another form of nebula, sometimes called supernova remnants. They have complex shapes with filaments and knots of gas curling through space. Within them, heavy elements forged in the interiors of stars are dispersed. The oxygen in the air you breathe, the calcium in your bones, the iron in your blood, all were formed in stars long ago and then released into space by events such as these. In that sense, every quiet breath you take connects you to ancient stars that lived and died before the Earth existed. As your body relaxes and your thoughts slow, you can imagine yourself drifting between these different scenes. A calm star shining steadily in the darkness, a glowing nebula where new stars are forming, and a faint expanding bubble of gas left behind by a star that has ended its life. Each of these places is distant, but the physics that governs them is consistent and reliable. Gravity, pressure, temperature, and radiation all interact in ways that scientists have studied and described through observation and theory. The colors that appear in images of nebulae are not random decoration. They correspond to the way specific atoms and ions emit or reflect light. Hydrogen, the most abundant element in the universe, often produces a soft red glow in certain regions. Ionized oxygen can contribute shades of green or teal in some images. Dust, made up of tiny solid particles, can scatter and absorb light, causing some regions to appear dark and obscuring what lies behind them. In other areas, dust reflects starlight, creating patches of gentle blue. If you picture a famous stellar nursery, such as the Great Nebula in the constellation Orion, you might see towering shapes of gas and dust illuminated from within by young energetic stars. In reality, those towering structures are regions where denser material is slowly being eroded by radiation and winds from nearby stars. Over time, the shapes will change and eventually disperse, but for now they stand as sculptures carved by light and motion, marking locations where stars are still in the process of forming. Now, as your breathing stays slow and comfortable, imagine the scale of all this. The distance from one star to another is so great that light, which travels extremely fast, can take years to cross the gap. The star that appears next to another in the sky might be a completely different distance from you, only appearing close because of the way the sky projects three-dimensional space onto a two-dimensional dome. Yet from the perspective of someone lying on their back and looking up, the effect is simple and soothing. A scattered pattern of lights, gently twinkling in the darkness. This twinkling is not a property of the stars themselves, but of the air above you. Starlight passes through layers of the atmosphere that constantly move and shift, like slow waves in a transparent ocean. These small changes bend the light slightly and cause the stars to appear to shimmer. In space above the atmosphere, stars do not twinkle in this way. Their light remains steady and constant, undisturbed by the subtle currents of air. Nebulae, too, when viewed through telescopes or captured by sensitive cameras, reveal details that the human eye alone cannot see. Long exposures gather more and more light over time, allowing faint structures to emerge. Astronomers sometimes map different wavelengths of light, including those invisible to the eye, into visible colors. This practice creates images that are both scientifically useful and visually striking, revealing structures in gas and dust that correspond to temperature, composition, and energetic events. As all these images are brought to mind, notice how they share a slow quality. Stars take millions or billions of years to change significantly. Nebulae evolve over long spans of time as gas flows, collapses, or disperses. Even the most dramatic cosmic events take place against a background of vast timescales. This slowness can be comforting. While daily life on Earth may feel fast or crowded, the universe beyond the atmosphere moves at a pace that is serene and steady. You are at this moment a small part of that universe, resting on a planet that orbits a single star in a galaxy filled with hundreds of billions of stars. Around you, life has emerged and evolved using atoms that were forged in stars. Above you, beyond the sky, stars and nebulae continue their long cycles. Gas collapsing, stars igniting, shining, and eventually returning their material to space. It is a continuous process, an ongoing transformation of matter and energy that stretches across cosmic time. As this introduction comes to a gentle pause, you can let your attention rest on a single point of light in your mind. Imagine one quiet star, shining steadily, far out in the darkness. Around it lies the faint glow of distant nebulae, soft and diffuse. Everything is quiet here. Everything is unhurried. In the next part of this journey, the story will move more deeply into what stars are, how they live, and how nebulae cradle both their beginnings and their endings. But for now, you can simply rest in the calm presence of that distant, steady light. What stars really are. Imagine that your awareness drifts a little closer to one of the stars that has been quietly shining in the sky above you. From far away, it is only a tiny point of light, something that could almost be covered by the tip of a fingertip held at arm's length. Yet as you move closer in your mind, that small point expands into a vast glowing sphere of gas, so large that it could contain many planets like Earth deep within it, and so bright that its light spills out into the surrounding darkness in all directions. A star is not a solid object. If you could somehow hover near its surface, there would be no place to stand, no solid ground to touch. Instead, you would find an enormous ball of hot gas, held together by its own gravity. The gas is mostly hydrogen, the simplest and lightest element, with a significant amount of helium and smaller traces of heavier elements. Under the pull of gravity, this gas is compressed toward the center, and as it is compressed, it grows hotter and denser. Deep inside the core of a star, conditions become extreme. Temperatures climb to many millions of degrees, and the pressure rises to incredible levels. In this environment, individual atoms move so quickly and collide so forcefully that their nuclei can merge. This process is called nuclear fusion. In most stars, during the long, stable part of their lives, hydrogen nuclei combine to form helium, and in doing so, a small amount of mass is converted into energy. This energy does not stay quietly in the core. It moves outward, carried by radiation, and in many stars by slow, churning currents of gas. Photons created in the core scatter again and again, absorbed and re-emitted in a long and winding journey outward through the dense interior. By the time they reach the outer layers and escape into space, they may have changed direction countless times. Eventually, some of that light travels across space and reaches a planet like Earth, where it can warm a surface, grow a plant, or simply illuminate a quiet night. The structure of a typical star can be imagined as a series of layers, not with sharp boundaries like the layers of an onion, but with gradual transitions from one region to another. At the center lies the core, where fusion takes place and energy is generated. Surrounding the core is a region where energy moves outward, mainly in the form of radiation. Farther out in many stars, there may be a convective region where hot gas slowly rises and cooler gas sinks in a very slow and steady circulation that helps transport energy toward the surface. The outermost visible region of a star, the part that emits most of the light we see, is often called its photosphere. This is not a solid surface, but rather a thin layer from which photons can escape into space more easily. Above this layer, there can be additional regions of thinner, hotter gas, which in some stars form a tenuous atmosphere that extends far outward. Even so, to distant observers, the star appears as a clean, simple point of light, its internal complexity hidden behind sheer distance. The balance that allows a star to exist for a long time is delicate and stable. Gravity constantly pulls its material inward, trying to make the star contract. At the same time, the energy produced by fusion in the core creates pressure that pushes outward. When these two influences match, the star is in a state of equilibrium. Its size remains roughly constant, and its overall behavior is steady. Most of the time during the main stage of a star's life, this balance holds remarkably well. If the rate of fusion increases slightly for some reason, the core can expand, which lowers the temperature and slows the fusion again. If the rate of fusion decreases, the core can contract a little, heating up and encouraging fusion to pick up. In this way, the star tends to regulate itself over long periods. The result from the outside is a quiet constancy. Night after night, year after year, a star's brightness and color stay almost the same, making it a reliable feature in the sky. The color of a star is closely related to its surface temperature. Cooler stars with lower surface temperatures emit more light at longer wavelengths and appear reddish. Stars with intermediate temperatures, like the Sun, appear more yellowish or white to the human eye. Hotter stars emit more light at shorter wavelengths and tend to look white or bluish. To the eye of a relaxed observer on a clear night, many stars may seem simply white, but sensitive instruments reveal subtle differences in color that carry information about their temperatures and other properties. The size of stars can vary widely. Some stars are only slightly larger than Earth, while others are hundreds of times wider than the Sun. Mass is one of the most important properties that determines how a star will evolve over its lifetime. A star with a relatively low mass will burn its fuel slowly, shining at a modest brightness for a very long time. A star with a higher mass will shine much more intensely, but use up its fuel more quickly, leading to a shorter life on cosmic timescales. For a listener drifting towards sleep, it can be soothing to think of stars not as random specks, but as individual objects, each following its own long path through time. A small, cool star, sometimes called a red dwarf, may shine quietly for tens of billions of years. In that time, entire civilizations could rise and fall on planets that might orbit it, and the star would continue its steady glow, almost unchanged. More massive stars go through their fuel more rapidly and end their lives much sooner. But even for them, the timescales are vast compared to human experience. When a star forms, it does not begin immediately as a fully structured object with a stable core and balanced layers. It starts as a contracting cloud of gas that gradually heats up as the central region grows denser and hotter. Fusion begins slowly and then strengthens, eventually providing enough outward pressure to halt further collapse. At that point, the star settles into the main and longest chapter of its existence, where hydrogen fusion in the core is the dominant source of energy. In this long middle phase, called the main sequence stage, the star's life is relatively uneventful from the outside. It shines at a nearly constant brightness, its color remains steady, and it follows a smooth path through space. Around such a star, planets can orbit in stable patterns, bathed in the light and warmth coming from the stellar surface. On at least one such planet, life has emerged and developed the ability to look back up at the sky and study these distant suns. Our own sun is an example of a main sequence star. It formed from a cloud of gas and dust in our galaxy, and for billions of years it has been quietly fusing hydrogen in its core. The energy released in these fusion reactions travels outward and eventually reaches Earth as sunlight. That sunlight drives weather patterns, supports plant life, and provides the warmth that makes the surface of our planet habitable. At the same time, the sun continues its own gradual, almost imperceptible evolution, slowly changing as it uses its fuel. When imagining stars, it can help to picture their variety. Some spin rapidly, completing a rotation in hours. Others rotate much more slowly, taking many days or even longer to turn once on their axis. Some stars exist alone, like the sun, while others are part of binary systems where two stars orbit around a common center, or even more complex multiple systems. In such cases, their gravitational dance can be intricate but still governed by the same basic physical laws. Even though the internal physics of stars involves high energies and dense matter, the overall description becomes gentle when viewed at a distance. The star simply shines. Its light spreads outward, traveling calmly in straight lines unless it meets gas, dust, or a planet in its path. Space around it is largely empty, so the light moves unimpeded for many years. Eventually, a tiny fraction of that light may be captured by the eye of an observer lying on a planet's surface, or by a telescope carefully aimed at the sky. The stability of stars over long durations has allowed astronomers to use them as reference points. Their positions and brightness can be measured, cataloged, and returned to over and over. Over very long time, stars do drift in their orbits around the center of the galaxy, and their positions change slowly. But on human timescales, constellations appear fixed. The familiar patterns traced out by bright stars on the sky become part of cultural stories and navigation methods. Behind each of those points of light, however, lies the same underlying reality. A vast, luminous sphere of gas held in equilibrium by the interplay of gravity and fusion. The life of a star is not static forever. Hydrogen in the core is gradually converted into helium. Over millions or billions of years, the composition changes, altering the conditions in the core and causing the star's structure to respond. Eventually, in most stars, the core can no longer sustain the same hydrogen fusion reactions that maintain the long, stable phase, and the star begins to enter a new chapter in its evolution. But that transition happens slowly, giving plenty of time for planets and any life upon them to experience the star in its long, stable form. For now, you can think of a star as a kind of cosmic hearth, quietly burning through its fuel, radiating warmth and light out into the cold of space. It does not rush. Its changes are measured in spans of time that dwarf human history. Whether it is a small, cool star glowing softly for a very long time, or a more massive, brighter star with a shorter life, each follows a pathway determined by its mass composition and the laws of physics that apply everywhere in the universe. As your body grows heavier with relaxation, it can be calming to imagine that above you, countless stars are following their own long, patient journeys. They formed from clouds of gas, they shine through fusion in their cores, and someday, far in the future, they will change and fade, returning their material to the wider galaxy. The same atoms that now make up your body once passed through such cycles. The iron in your blood, the calcium in your bones, and many of the elements around you were created in stars and then sent out into space, eventually becoming part of new clouds, new worlds, and new living things. In the next stage of this quiet journey, the focus will move more deeply into the clouds that surround and cradle stars. The nebulae. These are the places where stars are born, the regions where the material of old stars gathers again and prepares for new beginnings. For now, you can simply rest with the image of a single star in your mind, its core glowing with fusion, its surface radiating light, and its presence steady, calm, and enduring in the silence of space. Nebulae, the cosmic clouds. Let your thoughts drift now from the sharp, defined form of a star to something much softer and more diffuse. Picture a region of space where the darkness is not completely dark, but instead glows faintly with a pale, delicate light. This is a nebula, a vast cloud of gas and dust suspended in the space between stars. The word nebula comes from a Latin term meaning mist or cloud, and it captures the gentle, hazy quality of these structures when viewed through telescopes. Nebulae are not solid objects, and they are not dense in the way that matter on Earth is dense. If you could float within one, you would not feel enclosed or surrounded by anything you could touch. The gas is so thin that by Earth standards it would be considered an almost perfect vacuum. Yet when spread across distances measured in light years, even such tenuous material can contain many times the mass of the sun. It is the sheer scale that makes these clouds significant. The gas in a nebula is primarily hydrogen, the simplest and most abundant element in the universe. Alongside hydrogen, there is helium and smaller amounts of heavier elements like oxygen, nitrogen, carbon, and sulfur. Mixed in with the gas are tiny solid particles, grains of dust that are often smaller than a speck of pollen. These dust grains play an important role, absorbing and scattering light, and in some cases serving as surfaces where atoms can meet and combine into simple molecules. Nebulae come in several different types, each with its own character and appearance. Some nebulae shine brightly because they contain or are near young hot stars that flood the surrounding gas with ultraviolet light. This high-energy light can strip electrons from hydrogen and other atoms, leaving them ionized. When those electrons recombine with the atoms, they emit light at specific wavelengths, creating a glow that can be captured in images. These are called emission nebulae, and they often appear in shades of red and pink due to the light emitted by hydrogen. Other nebulae do not glow by themselves, but instead reflect the light of nearby stars. These reflection nebulae tend to appear bluish because blue light scatters more easily off the tiny dust grains than red light does. The effect is similar to the reason Earth's sky appears blue during the day. Shorter wavelengths are scattered more effectively than longer ones. Reflection nebulae are often found near bright stars, where starlight illuminates the surrounding dust and gas like a gentle lantern in fog. There are also dark nebulae, regions where dense clouds of dust block the light from stars or glowing gas behind them. These appear as shadowy patches or silhouettes against a brighter background. They do not shine or reflect, but their presence can be detected by the way they obscure other objects. In some cases, dark nebulae have intricate shapes with tendrils and curves that suggest slow, complex motions within the cloud. Another category is planetary nebulae, though the name is misleading. These nebulae have nothing to do with planets. Early observers looking through small telescopes saw them as round, disc-like shapes that reminded them of planets, and the name stuck. In reality, planetary nebulae are shells of gas cast off by certain types of stars near the end of their lives. The gas expands slowly outward, forming delicate symmetrical structures that glow because they are lit from within by the hot core of the dying star. Each type of nebula has its own visual and physical characteristics, but all share the quality of being spread out over enormous distances. A single nebula might span dozens or even hundreds of light years from one side to the other. Within such a vast volume, the density of matter is incredibly low, yet the total mass can be immense. It is this combination of size and low density that gives nebulae their ghostly, ethereal appearance. The colors seen in images of nebulae are not arbitrary or purely artistic. They correspond to the wavelengths of light emitted or reflected by different elements and compounds. Hydrogen, when ionized and then recombining with electrons, emits a specific red wavelength known as H-alpha. This is one of the most common sources of red color in emission nebulae. Oxygen, when ionized to different degrees, can emit green or blue-green light, depending on the conditions in the nebula. Sulfur emits in a different part of the spectrum, and nitrogen contributes its own set of wavelengths. Astronomers sometimes capture images of nebulae using filters that isolate specific wavelengths, and then assign colors to those wavelengths to create a composite image. In some cases, invisible wavelengths such as infrared or ultraviolet are mapped to visible colors so that details hidden from the eye can be revealed. The result is often a stunning multicolored view that shows structure and composition in the cloud, though the colors may not represent exactly what a human eye would see if it could somehow travel there. Despite the vividness of such images, the reality of a nebula is quiet and still. The gas moves, but it moves slowly, often at speeds of only a few kilometers per second. Compared to the speed of light, this is almost motionless. Over thousands or millions of years, the shape of a nebula can change as gas flows, expands, or collapses, but from moment to moment, everything appears frozen. In regions where nebulae are particularly dense, gravity can begin to pull material together. If a portion of the cloud becomes dense enough, it can start to collapse under its own weight. This is the first step in the formation of a star. The collapsing region heats up, and over time, if conditions are right, a new star ignites within the cloud. In this way, nebulae serve as stellar nurseries, places where the next generation of stars is born from the remnants of previous generations. Some of the most famous nebulae visible from Earth are sites of active star formation. In these regions, clusters of young stars are often found, still embedded in or emerging from the clouds that gave birth to them. The intense radiation and stellar winds from these young stars sculpt the surrounding gas, carving out cavities and shaping the nebula into complex forms. Over time, the stars disperse the cloud, and eventually the nebula fades, leaving behind a new cluster of stars. Other nebulae mark the end of a star's life rather than its beginning. When certain stars exhaust their fuel, they swell up and then gently cast off their outer layers into space. These layers expand outward, forming a shell or ring around the remaining core. The core itself, now exposed and very hot, emits ultraviolet light that causes the expanding shell to glow. This creates a planetary nebula, a brief and beautiful phase in the stellar life cycle that lasts only a few tens of thousands of years before the gas disperses and becomes too thin to see. There are also nebulae formed by more violent events. When a massive star ends its life in a supernova explosion, the outer layers are blasted into space at high speed. This ejected material forms an expanding shell of hot gas, often with intricate filaments and knots where the material has been compressed by shock waves. These supernova remnants can glow brightly for thousands of years, gradually fading as they expand and cool. They are important sites for the production and dispersal of heavy elements, enriching the surrounding medium with the building blocks for future stars and planets. The dust mixed in with the gas plays a subtle but important role. Dust grains can absorb starlight and re-emit it at longer wavelengths, warming the surrounding gas. They can also act as tiny seeds for the formation of molecules, providing surfaces where atoms can meet and bond. In the densest and coldest parts of nebulae, complex molecules can form, some of them organic in nature. These molecules, though present in very small amounts, are of great interest because they hint at the chemical pathways that might lead to life. In certain dark, dense clouds, the temperature can drop to only a few degrees above absolute zero. In such cold environments, molecules like carbon monoxide, water, and even more complex organic compounds have been detected. These molecular clouds are among the coldest places in the universe, and yet they are also among the most fertile, serving as the sites where new stars and planetary systems are formed. When you imagine floating through such a cloud, there would be no sensation of cold, because the gas is so thin that it could not transfer much heat to or from your body. There would be no wind, no sound, and no visible boundary. Just a faint glow, perhaps, or a slight dimming of distant starlight. If you were to look in one direction, you might see the light of a nearby star illuminating the gas, giving it a soft, diffuse radiance. In another direction, the cloud might appear dark, blocking the view of stars beyond. The shapes of nebulae can be strikingly varied. Some appear as smooth, rounded clouds. Others have intricate branching structures that resemble rivers or veins. Still others show symmetrical patterns, suggesting that the processes shaping them have a certain regularity or balance. These shapes are sculpted by the interplay of gravity, radiation pressure, stellar winds, and magnetic fields, all acting over immense spans of time. In regions where star formation is happening, the presence of many young stars can create a complex environment. Ultraviolet light from hot stars ionizes the surrounding gas, creating glowing regions. Stellar winds push material outward, compressing nearby gas and sometimes triggering further collapse and star formation in neighboring areas. This feedback between stars and the surrounding nebula can lead to waves of star formation spreading through a cloud over millions of years. To the observer lying quietly and listening, the image of a nebula can be a source of calm. It is a place where matter gathers slowly, where light and gravity interact gently over vast distances, and where the processes of creation and dispersal unfold with patience. There is no urgency in a nebula, no sudden movement. Everything happens in its own time, governed by physical laws that operate the same way everywhere. The connection between stars and nebulae is continuous and circular. Stars form from nebulae, drawing material inward and condensing it into dense, hot cores. They shine for long periods, altering the surrounding gas with their light and winds. Eventually, they return material to space, either gently through stellar winds and the casting off of outer layers, or more dramatically through supernova explosions. This returned material mixes back into the interstellar medium, enriching it with heavier elements, and eventually becomes part of new nebulae where future stars will form. In this way, nebulae are not just passive clouds. They are active participants in the life cycle of matter in the galaxy. They are reservoirs of raw material, sites of transformation, and markers of both beginnings and endings. To see a nebula in an image or through a telescope is to witness a stage in an ongoing process that has been repeating for billions of years and will continue for billions more. As your breathing remains slow and even, you can let the image of a glowing nebula settle in your mind. Picture soft curtains of gas, faintly luminous, stretching across light years of space. Imagine the subtle gradations of color, the delicate threads and wisps, and the quiet presence of stars scattered within or nearby. This is the environment in which stars are born, the setting for some of the most important processes in the universe, and yet it is also a place of profound stillness and beauty. In the next part of this journey, the focus will turn to the process of star birth itself, the long and gradual transformation of a cold, dense knot of gas into a shining, stable star. For now, you can rest with the thought of nebulae as the great cradles of the cosmos, holding the material that will one day shine as new suns. Star birth in molecular clouds. Imagine now that your awareness drifts deeper into one of these vast nebulae, into a region where the gas is denser and colder than the surrounding space. This is a molecular cloud, a place where the material has gathered together more closely and where temperatures have dropped to near absolute zero. In such conditions, atoms move slowly, and many have bonded together to form simple molecules. Hydrogen, which normally exists as individual atoms in hotter regions, here combines into molecular hydrogen, two hydrogen atoms linked together. These molecular clouds are enormous. A single cloud can stretch across hundreds of light years and contain enough mass to form thousands of stars. Within the cloud, there are denser clumps and cores, regions where gravity has begun to concentrate the material even further. It is in these dense cores that stars are born, slowly and quietly over the course of millions of years. The process begins with a slight increase in density. Perhaps a passing shock wave from a nearby supernova compresses part of the cloud, or perhaps random motions within the cloud cause material to drift together. Whatever the trigger, once a region becomes dense enough, its own gravity starts to pull in more material from the surroundings. As more gas falls inward, the density increases further, and the gravitational pull becomes stronger. This is the start of gravitational collapse. At first, the collapsing region is still very cold, and the material falls inward relatively freely. The cloud fragments into smaller pieces, each of which may eventually form a star or a small group of stars. As the material in one of these fragments continues to fall inward, it begins to heat up. The gravitational energy of the infalling gas is converted into thermal energy, raising the temperature at the center. Over time, a dense core forms at the center of the collapsing region. This core is still surrounded by a larger envelope of gas and dust that continues to fall inward. The core itself grows hotter and denser as more material accumulates. At this stage, the object is called a protostar, a star in the process of forming but not yet hot enough in its core to sustain nuclear fusion. The protostar is hidden from view at visible wavelengths because it is deeply embedded in the cloud of gas and dust. The dust absorbs the visible light emitted by the warm protostar and re-radiates it as infrared light, which can pass more easily through the cloud. Astronomers studying star formation often use infrared telescopes to peer into these regions and observe the protostars within. As the protostar continues to accumulate mass, a disk of material forms around it. This disk, called an accretion disk, is made of gas and dust that did not fall directly onto the protostar but instead settled into a flattened, rotating structure. Material in the disk gradually spirals inward, eventually joining the growing protostar. The disk can extend for hundreds of astronomical units, far beyond the scale of planetary orbits in a mature solar system. Within the accretion disk, particles of dust collide and sometimes stick together. Over time, these small clumps can grow into larger bodies. This is the beginning of planet formation, though that process will take much longer to complete. For now, the disk is a swirling ring of material, slowly feeding the central protostar and gradually evolving as the system matures. The protostar itself is not yet a true star. It glows because it is warm, heated by the energy released as material falls onto it. But it is not yet generating energy through fusion. Deep in its core, the temperature and pressure are rising, but they have not yet reached the levels needed to start fusing hydrogen into helium. This phase can last for hundreds of thousands or even millions of years, depending on the mass of the protostar. Eventually, if the protostar has accumulated enough mass, the core temperature climbs to several million degrees. At this point, hydrogen nuclei begin to collide with enough energy to overcome their mutual repulsion and merge together. Nuclear fusion begins, and the protostar becomes a true star. The energy released by fusion creates an outward pressure that balances the inward pull of gravity, and the star settles into a stable state. This transition marks the beginning of the main sequence phase, the long, stable period during which the star will shine steadily by fusing hydrogen in its core. For a star like the Sun, this phase can last about 10 billion years. For smaller stars, it can last even longer. For more massive stars, the main sequence phase is shorter but still measured in millions of years. Not all collapsing clouds produce single stars. In many cases, a cloud fragments into multiple cores and a group of stars forms together. These stars may remain loosely bound to each other as an open cluster, or they may drift apart over time as they orbit the galaxy. Some collapsing regions form binary or multiple star systems where two or more stars orbit around a common center. The details depend on the initial conditions in the cloud, including its mass, rotation, and turbulence. During the protostellar phase, the forming star can also produce powerful outflows and jets. These are streams of gas ejected at high speed along the rotation axis of the system. The mechanism that drives these jets is complex and involves magnetic fields and the interaction between the protostar and its accretion disk. The jets can extend for light years, plowing into the surrounding cloud and creating shock waves that heat and compress the gas. These outflows play an important role in regulating the growth of the protostar. They carry away some of the material and angular momentum that would otherwise fall onto the star, preventing it from spinning too rapidly. They also help clear out the surrounding gas and dust, eventually revealing the young star to direct observation. Young stars, especially those that are more massive, can be highly variable and energetic. They may flare up suddenly, increasing in brightness, or they may produce strong stellar winds that push away nearby material. Over time, as the star settles into its main sequence phase, this activity calms down, and the star becomes more stable and predictable. The timeline of star formation is long by human standards, but quick on cosmic scales. From the initial collapse of a dense core to the ignition of fusion can take a few million years for a star like the Sun. For more massive stars, the process can be faster, sometimes taking only a few 100,000 years. For less massive stars, it can take longer, but in all cases, the process is gradual, with each stage blending smoothly into the next. The environment around a forming star is rich and complex. The accretion disk may contain ices, rocky grains, and organic molecules. As planets begin to form within the disk, these materials are incorporated into the growing bodies. The composition of the disk, which depends on the composition of the original molecular cloud, will influence the types of planets that eventually form. In some regions of a molecular cloud, many stars form at roughly the same time. These clusters of young stars can number in the hundreds or thousands. The Orion Nebula, one of the most famous star-forming regions visible from Earth, contains a young cluster of stars that is still partially embedded in the gas and dust from which they formed. Observations of such regions provide valuable insights into the processes and timescales of star formation. As you listen and relax, you can picture a dense, dark cloud slowly contracting. Within it, a knot of gas collapses, heating up and beginning to glow faintly in the infrared. Around the forming protostar, a disk of material swirls gently, feeding the growing object at its center. Over millions of years, the core grows hotter. The surrounding envelope thins, and eventually a new star ignites, adding its light to the galaxy. This process has happened countless times throughout the history of the universe. Every star in the night sky, including the Sun, was born in a similar way, from a collapsing cloud of gas within a nebula. The stars you see tonight formed at different times in different places, but they all share this common origin. The dust and gas that remain in the disk around a young star can eventually coalesce into planets, moons, asteroids, and comets. In the case of our own solar system, this process led to the formation of Earth and the other planets. Some of the water on Earth and many of the organic molecules that are the building blocks of life may have originated in the cold molecular cloud from which the sun formed. There is something deeply calming about the slowness and inevitability of star formation. Gravity acts patiently, pulling material together over immense spans of time. Temperature and pressure rise gradually, step by step, until the conditions for fusion are met. The process does not rush. It unfolds according to physical laws, and those laws operate the same way in every star-forming region in the universe. For a listener drifting towards sleep, the image of a protostar can be soothing. It is warm, glowing softly, surrounded by a disk of slowly swirling material. It is hidden within a cloud, cocooned and protected. Over time, it will emerge as a bright, stable star, but for now it is still in its earliest, quietest phase, growing steadily in the darkness. The connection between molecular clouds and stars is direct and essential. Without these clouds, stars would not form, and without stars, the universe would remain dark and cold. The clouds themselves are made of material that was once part of earlier stars, enriched with heavier elements produced in stellar cores and dispersed by stellar winds and supernovae. This cycling of matter from cloud to star and back again is one of the fundamental processes that shapes the structure and evolution of galaxies. As your breathing remains slow and your body sinks deeper into relaxation, you can hold the image of a molecular cloud in your mind. Within it, countless dense cores are collapsing, each one a potential future star. Some will become small, dim stars that will shine for trillions of years. Others will become bright, massive stars with shorter but more dramatic lives. All of them are following the same basic path, from gas and dust to fusion and light. In the next section, the focus will shift to the main sequence, the long, stable phase of a star's life when it shines steadily and reliably. This is the phase in which most stars spend the majority of their existence, and it is the phase that makes life on planets possible. For now, you can simply rest with the image of a star being born, a small, warm glow emerging slowly from the cold darkness of a molecular cloud. The main sequence, a star's long life. Once fusion begins in the core of a newly formed star, a profound change takes place. The star is no longer dependent on the energy released by gravitational contraction. Instead, it draws its energy from the conversion of hydrogen into helium, a process that can sustain it for billions of years. This marks the beginning of the main sequence phase, the longest and most stable period in the life of most stars. The term main sequence comes from the way stars are organized on a diagram that plots their brightness against their temperature. When astronomers plot thousands of stars on such a diagram, most of them fall along a diagonal band that stretches from cool, dim stars in the lower right to hot, bright stars in the upper left. This band is called the main sequence, and stars on it are all doing the same thing, fusing hydrogen into helium in their cores. For a star like the Sun, the main sequence phase lasts approximately 10 billion years. Our Sun is currently about halfway through this phase, having been shining steadily for roughly 4.5 billion years. It has another 5 billion years or so before it exhausts the hydrogen in its core and begins to evolve into something different. During this entire time, the Sun's brightness and temperature remain remarkably constant, changing only very slowly. Smaller stars, those with less mass than the Sun, burn their fuel even more slowly. They have lower core temperatures and lower fusion rates, so they shine more dimly and use up their hydrogen over much longer periods. Some of the smallest stars, called red dwarfs, can remain on the main sequence for tens or even hundreds of billions of years. In fact, the universe is not yet old enough for any red dwarf to have exhausted its hydrogen supply. Every red dwarf that has ever formed is still in its main sequence phase today. On the other end of the scale, more massive stars burn through their hydrogen much more quickly. These stars have higher core temperatures and higher fusion rates, so they shine very brightly but use up their fuel in only a few million years. The most massive stars can complete their main sequence phase in just a few million years, a blink of an eye in cosmic terms. Their brightness comes at the cost of a short life. The balance that keeps a main sequence star stable is delicate but robust. Gravity pulls inward, trying to compress the star. The pressure from the hot gas in the core, heated by fusion, pushes outward. When these two forces are equal, the star neither expands nor contracts. It remains in a state called hydrostatic equilibrium, where its size and structure are stable over long periods. If something were to disturb this balance, the star would naturally adjust. If the fusion rate increased, the core would heat up and expand slightly, which would lower the temperature and slow the fusion back down. If the fusion rate decreased, the core would contract, heating up and increasing the fusion rate again. This self-regulating mechanism is one reason why stars can shine steadily for such long times. The fusion process itself is elegant in its simplicity. In the cores of main sequence stars like the Sun, hydrogen nuclei, which are simply protons, collide and merge through a series of reactions. The most common pathway involves several steps, starting with two protons combining to form a deuterium nucleus, a positron, and a neutrino. The deuterium then fuses with another proton to form a helium-3 nucleus, and eventually two helium-3 nuclei combine to form helium-4, releasing two protons in the process. The net result is that 4 hydrogen nuclei are converted into one helium nucleus, and a small amount of mass is transformed into energy according to Einstein's famous equation. This energy is released in the form of photons and neutrinos. The photons carry most of the energy and begin their long journey outward through the star, while the neutrinos escape almost immediately, passing through the star as if it were transparent. The journey of a photon from the core to the surface is surprisingly slow. Because the interior of the star is so dense, photons are constantly absorbed and re-emitted by atoms, changing direction each time. They take a random walk, scattering in all directions. It can take tens of thousands of years for the energy produced in the core to work its way to the surface and be radiated into space as light. By the time you see sunlight on a clear day, the energy in that light was produced deep in the sun's core many thousands of years ago. The structure of a main sequence star can be divided into zones based on how energy is transported. In the innermost region, the core, fusion produces energy. Surrounding the core is the radiative zone, where energy moves outward primarily through radiation, as photons are absorbed and re-emitted countless times. In stars like the Sun, there is also an outer convective zone, where energy is carried by the actual movement of gas. Hot gas rises toward the surface, cools, and then sinks back down, creating a slow, churning circulation. This convective motion is responsible for some of the activity seen on the surfaces of stars. On the Sun, convection creates a granular pattern on the photosphere, with each granule representing the top of a convection cell. Convection also plays a role in generating magnetic fields, which can lead to features like sunspots, solar flares, and prominences. These phenomena are signs of the dynamic nature of the sun's outer layers, even though the core remains stable and steady. The energy output of a main sequence star is closely tied to its mass. A star with twice the mass of the sun does not shine twice as brightly. Instead, it shines much more brightly, often 10 times or more. This is because the higher mass leads to higher core temperatures and pressures, which dramatically increase the fusion rate. The relationship between mass and luminosity is steep, meaning that small differences in mass can lead to large differences in brightness. This relationship also means that massive stars exhaust their fuel much more quickly than their lower mass counterparts. A star 10 times the mass of the sun might shine 1,000 times more brightly, but it will run out of hydrogen in its core in only about 20 million years. A star with half the mass of the sun, on the other hand, might shine for 50 billion years or longer. During the main sequence phase, the star's composition gradually changes. Hydrogen in the core is converted into helium, and the helium accumulates there, unable to fuse at the temperatures and pressures present in a main sequence star. Over time, the core becomes increasingly rich in helium, while the surrounding layers remain mostly hydrogen. This gradual shift in composition does not immediately cause dramatic changes, but it sets the stage for the next phase of the star's evolution. For billions of years, a main sequence star like the Sun remains an almost unchanging presence in its region of the galaxy. Planets, if they exist, orbit in stable patterns. The star's light and heat remain consistent, allowing for stable climates and, in at least one case we know of, the development and evolution of life. The reliability of the sun's energy output is one of the reasons Earth has been habitable for billions of years. There is something deeply soothing about the steadiness of the main sequence. While the universe around a star may be dynamic, with nebulae forming and dispersing, with other stars being born and dying, the main sequence star itself simply continues to shine. It does not flicker or fade. It does not suddenly change color or brightness. It follows a predictable path, governed by the same physical laws that apply everywhere. For a listener drifting towards sleep, the image of a main sequence star can serve as a point of calm stability. Picture the sun, a sphere of hot gas glowing steadily in the darkness of space. Deep in its core, fusion reactions proceed at a constant rate, releasing energy that will take thousands of years to reach the surface. The outer layers circulate slowly, carrying heat upward. The surface radiates light and warmth in all directions, a gentle, constant outpouring of energy. Around this star, planets follow their orbits, each one tracing the same elliptical path again and again. On one of those planets, life has emerged and evolved, shaped by the steady light of the star. Seasons change, tides rise and fall, and day follows night, all in rhythm set by the star and the planet's motion. Through it all, the star continues to shine, unchanged on timescales that matter to living things. This long stability is not unique to the Sun. Across the galaxy, billions of stars are in their main sequence phase, each one quietly fusing hydrogen and shining with a steady light. Some are cooler and dimmer, glowing with a deep red color. Others are hotter and brighter, shining white or blue. But all are following the same basic process, balanced between gravity and pressure, converting mass into energy in their cores. The main sequence is not eternal, however. Eventually, the hydrogen in the core runs low. The fusion rate slows, and the balance that has kept the star stable begins to shift. What happens next depends on the star's mass, but for all stars, the end of the main sequence marks the beginning of a new and very different chapter. For now, though, you can rest with the image of a star in its prime, stable and shining, a beacon of constancy in the ever-changing cosmos. Its core is hot and bright, its surface glows with a warm light, and its energy spreads outward, traveling across space to illuminate planets, moons, and the gas and dust of surrounding nebulae. In the next part of this journey, the focus will turn to what happens when the hydrogen runs out, when the core can no longer sustain the fusion that has powered the star for so long. The star will begin to change, swelling and cooling, entering a phase called the red giant stage. But that transformation is still far in the future for most stars. For now, they shine on, patient and enduring, lighting the darkness with their steady glow. Quiet, closing reflection. All through this quiet journey, stars and nebulae have appeared not as distant abstractions, but as calm, patient participants in a very long story. Stars are born in cold molecular clouds, shine steadily for millions or billions of years, and eventually return their material to space in slow winds, delicate planetary nebulae, or powerful supernovae. Nebulae, in turn, gather this material, cradle new stars, and carry the chemical record of everything that came before. You have drifted through dark, dense clouds where new stars are just beginning to form, almost imperceptibly over spans of time that make human lifetimes feel like brief, gentle breaths. You have rested beside stable main sequence stars, where the balance of gravity and fusion creates long epochs of quiet light. You have watched stars expand into red giants, shedding their outer layers in slow, luminous waves, and then condense into small, dense white dwarfs that cool in dignified silence. You have seen massive stars end in brilliant supernova, scattering the elements of future worlds outward in expanding shells, leaving behind neutron stars or black holes as compact reminders of their former presence. Nebulae have appeared around you as soft, glowing clouds, sometimes lit from within by young hot stars, sometimes silhouetted as dark shapes against brighter regions of gas. Star-forming regions like the Orion Nebula and the Eagle Nebula have shown how radiation and gravity sculpt cold gas into columns, arcs, and cavities. Planetary nebulae such as the Ring Nebula and the Helix Nebula have revealed the graceful endings of sun-like stars, their shells of gas expanding outward while their cores cool slowly at the center. Supernova remnants like the Crab Nebula and the Veil Nebula have shown how even violent endings become, at larger scales and longer times, part of a slow and continuous transformation. Throughout this, one theme is repeated in many forms. The universe does not waste matter. Hydrogen and helium from the early cosmos condensed to form the first stars. Those stars created heavier elements in their cores and in their depths, and returned those elements to space. New stars formed from enriched clouds, and around some of those stars, planets condensed, built from carbon, oxygen, silicon, iron, and many other elements. On at least one of those planets, some of that matter organized itself into living cells, into complex organisms, into minds capable of wondering about stars and nebulae while slowly drifting towards sleep. Every breath you take contains oxygen atoms that were once inside stars. The calcium in your bones, the iron in your blood, the carbon structures in your cells, all trace their history back through nebulae, through earlier generations of stars, through planetary nebulae and supernova remnants. You are not separate from the universe you have been imagining. You are one of the recent outcomes of the same processes that light the night sky. As you lie here now, breathing slowly and evenly, the galaxy continues its quiet work. In some distant region, a molecular cloud is collapsing and a new protostar is beginning to glow in infrared light. Elsewhere, a stable star continues its long main sequence life, its light illuminating worlds that may be home to their own forms of life. In another corner of the galaxy, a red giant is gently casting off its outer layers, creating a new planetary nebula that will briefly shine before blending into the surrounding gas. Far away, a massive star has just ended its life in a supernova, and its expanding shell is beginning the long task of enriching its surroundings. On timescales that matter to you tonight, none of this will change quickly. The stars will hold their places in the sky. The nebulae will remain as they are, shifting so slowly that even many generations of observers would see only subtle differences. The cycles of birth and death, of collapse and dispersal will continue, but they will do so at a pace that feels almost motionless compared to the rhythms of a single human life. If you like, you can imagine a single calming scene to carry with you into sleep. Perhaps it is a wide field of stars, scattered across a dark sky with one faint misty nebula glowing softly near the center of your view. The stars twinkle slowly through an atmosphere that shields and softens their light. The nebula does not flicker, it simply glows, a steady presence in the background. Nothing demands attention, nothing changes abruptly. The scene is gentle, stable, and quiet. With each exhale, you can let your attention rest a little more lightly on that image. There is no need to hold on to any particular fact or detail now. You have already traveled through the structure of stars, the types of nebulae, the processes of star birth and star death, and the long cycles that connect them. All of that can now fade into a simple, soft feeling that the universe is vast, ancient, and patient, and that you are safely within it, made of the same materials, following your own much shorter but still meaningful path. If any thought arises, you can let it pass through like a small cloud moving across a large, quiet sky. The larger view remains, stars shining steadily, nebulae glowing softly, matter cycling slowly from one form to another. There is nothing you need to solve, nothing you need to remember. The science is still there, but now it can rest in the background, like starlight that has already crossed the darkness and arrived, needing no further effort. As this journey closes, you might notice that your breath is slow and calm, your body heavy and supported, your mind quieter than when you began. If your eyes are closed, you can keep the soft image of distant stars and nebulae in the background of your awareness, or you can let even that image dissolve into simple darkness. Sleep, when it comes, will arrive naturally and in its own time, just as stars form and evolve in their own time, without haste. If you have enjoyed this quiet exploration of sleepy facts about stars and nebulae, and would like to drift through more gentle journeys into science in the future, you are warmly invited to return, to listen again, and if you wish, to like and subscribe in your own time and your own way. For now, there is nothing more you need to do. Just rest, breathe, and let the quiet light of distant stars keep you company as you drift towards sleep.